morning, guys. Welcome to a new lesson on the use of slope deflection methods of structural analysis. My name is Engineer Dr. Edidiongi Ambrose from the Department of Civil Engineering at Akwa State University. And so we'll be looking at the slope deflection method of structural analysis. Remember, in our previous lesson, we were using the method of moment distribution to analyze statically indeterminate structure. So in our lesson for today, we are using the slope deflection method to analyze statically indeterminate structure. And so let's continue. So the slope deflection method is an alternative technique for the analysis of statically indeterminate structures. And the solution involves deriving and finding solution to a set of simultaneous equations. And once you've derived a set of simultaneous equations, when you solve them, you are able to find the support moment. And so when you find the support moment, you are done. You are done. So the more sizable and complex the structure is, the more equations we will have to solve. And so hence this method is only possible to manually solve structures with limited size, especially with limited number of unknown joint rotations. However, this method can be adopted such that the equations are solved with the use of computer applications using softwares. And in fact, this method is the basis for modern computer techniques in structural analysis. So most of those software that analyze structures, they use this method because they just program the system to derive a set of simultaneous equations and then find solutions to them. Of course, you know the computer is able to solve a set of simultaneous equations with so many unknown, unlike doing it manually. So let's look at the basic steps in slope deflection method. So these are the basic steps. The first step is that for each span of a beam, as shown beside, write down slope deflection equation for the end moment. The end moment are the support moment, not fixed end moment. Note. So if L is a span of a beam, if you have a beam like this, and L is a span of the beam AB, and you have, this is the deflection shape of the beam. Of course, it's not always obvious like this. This is exaggerated for the sake of what we want to do. And once you have this deflected shape, you draw the tangent to it. From there, you can have the rotation at A and the rotation at B. And if EI is the flexural rigidity of the beam, and then you can, of course, you can write fixed end moment at joint A and fixed end moment at B. So if you have all those things, the theory says that the support moment at AB is equal to 2EI over L into 2 theta A plus theta B minus 3 delta over L plus or minus the fixed end moment at AB. Now, delta here is support settlement. That is for situations that there are support settlement. Delta stands for support settlement. And so when you want to write the fixed end moment, the support moment at B, support B going to A, it is become this 2EI over L into theta A. Notice that in this case, because you're at joint B, theta A is not multiplied by 2B. In this case, theta B is multiplied by 2. So minus 3 delta over L plus or minus the fixed moment at that support. So it takes when you are at theta A, when you are at support A, theta A is multiplied by 2. The other theta is not. When you are at support B, the other theta is not multiplied by 2 and theta B is multiplied by 2. So once you are able to derive that slope deflection equation, so what you now do is that at each joint, where joint rotation occur, you identify the equilibrium condition, and the equilibrium condition require that the sum of the two internal moments at the joint should sum to 0 or to the value of the external joint moment if there is any such moment. Now doing this will generate a set of simultaneous equations. note that you must obtain one equation for each joint that is free to rotate. So any joint that is not fixed, you must derive one equation for them. Now solve the generated simultaneous equation for the unknown joint rotation. And once you solve them, you back substitute the calculated joint rotation, that is theta A, theta B, theta C, as the case may be. You back substitute them into the original set of slope deflection equation that you have generated in step 1. Once you do that, you will get the end moment in each span, and then determine the support reaction, the span moment, the shear force, and the bending moment diagram. Another thing to note is that this method, once you are able to calculate the support moment, the rest will just be like a moment distribution, the determination of support reaction, and drawing of shear force and bending moment diagram. They are the same thing. So the difference is just that this method helps you. The difference in the two methods is just two different ways of finding the support moment. Okay, take note of this. We did this in moment distribution. They are the fixed end moment for common load cases. So if you have a UDL acting across the span AB, the fixed end moment at the left support, which is support A, is minus WL squared over 12. At the right support is WL squared over 12. Then if you have a uniformly varying load, at the A, support A is minus WL squared over 30, and support B is WL squared over 20. Also take note, like I said in moment distribution, if this load was laterally inverted, that means where the maximum load was at this side, this place will still carry the minus because it is left support, but the value will be WL squared. So this place will now be WL squared over 20, while this other side will now be WL squared over 30. Sorry, this place will be minus WL squared over 20. This place will be WL squared over 30. So when you have a point load acting at mid-span, you have this at the left support and this at the right support. When you have a point load that is not at mid-span, you have this minus BAB squared over L squared, BA squared B over L. Take note of that. These are the fixed end moments. So quickly, we go into example 1. The first example is that we should analyze this beam and draw the bending moment and shear force diagram. If you remember very well, this is example 2 that we use in moment distribution method. It is example 1 here. So let's go to the solution together. The first thing to note is that there is no support settlement. And because there is no support settlement, delta equals to 0 for all support. Take note of that. So we will go ahead to calculate the fixed end moment. The fixed end moment, for calculating fixed end moment, remember all this formula. This is what we are going to use for those different cases. And so the fixed end moment at A, this is span AB, at A going to B, that's fixed end moment at AB. Because this span is acted by a point load at mid-span. So at the left support is minus PL over 8. So in this case, the P is 40, L is 8 over 8. So it gives you minus 40 kilonewton meter. At the right hand side of that support AB, you have F fixed end moment B going to A. So that is what you have here. And in that case, it will be PL over 8, not minus, just PL over 8. So P is 40, L is 8. You calculate that, it gives you 40 kilonewton meter. This other one was minus 40, this one is plus 40. So you go to span BC. When you go to span BC, there is a UDL there. So at the left hand side, we call it fixed moment at B going to C is going to be minus WL squared over 12, where W is 24 and L is 4. If you put them, it becomes minus 32. At the right support of that span BC, you have WL squared over 12, not minus, but plus. So you do that gives you 32. Then span CD, the left side, this place, we have a point load at mid-span. So at BC going to D, you'll have minus PL over 8, the same thing that we had in AB. So minus PL over 8, where P is 20, L is 8. So that gives you minus 20 kilonewton meter. And so you go again at support D in span CD. The fixed moment is PL over 8, and that equals to 20 kilonewton meter. And so the next thing we are going to do is to generate the slope deflection equation. So remember this general slope deflection equation. That's what we are going to use to generate the slope deflection equation for each support moment. So let's start with AB. Support moment AB, that is MAB, is equal to, the equation is 2EI over L, 2 theta A plus theta B minus 3 delta over L plus or minus the fixed moment. But take note that theta A, okay, is what is multiplied by 2. So we go ahead. Also note that delta is 0 because of no support settlement. So that means the whole of this component is gone. So that's why when you come to MAB, you have 2EI over 8, which is L, into 2 theta A plus theta B. The fixed end moment was minus 40, so you substitute the fixed end moment here, minus 40. So this gives us equation for support moment at A going to B. When we go to the support moment at B going to A, we are still in span AB. So when we go B going to A, we are still going to use a similar equation like this. So it's 2EI over L. Of course, L is 8. So 2EI over L into, because you are theta B, theta A is not multiplied by 2, but theta B is multiplied by 2. The fixed end moment day was plus 40 here. So you notice that this plus or minus depends on the value carried by the fixed end moment. So let's go to BC. Moment at B. We are now in span BC. So B going to C, that is this place. So we're going to be 2EI over L. L day is 4. And because we are at this theta B, when we are here at joint B, theta B will be multiplied by 2. Theta C is not multiplied by 2. And the fixed end moment day was minus 32. So we have minus 32. We come to CD. C going to D. Of course, the same 2EI over L. L is 4. Because it's theta B, it's theta C. Theta B is not multiplied by 2. Theta C is multiplied by 2. And so plus the fixed end moment, which is 32. And then we go to MCD. MC going to D is the same 2EI over L, because we are theta C. So theta C we are joint C. Theta C is multiplied by 2 plus theta D, and that is a fixed end moment minus 20. And we do the same to the support, the moment at D. And so after this, what we have to do is to do what we call joint equilibrium. So to handle the joint equilibrium, the first thing you will need to know, let's see something. If you notice, joint A and joint D are fixed. And when the joint is fixed, there is no joint rotation. So that gives us information that theta A, which is supposed to be rotation at joint A, and theta D, which is supposed to be the rotation at joint D, they are all 0. And so when they are all 0, what it tells us now is that out of theta A, theta B, theta C, theta D, theta A and theta D, they are known, they are 0. So what we now have is theta B and theta C. There's a joint rotation at B and C. That means we have 2 unknown joint rotations, and of course we will need 2 equations to be able to solve those 2 unknown. Take note of that. So we go to do the joint equilibrium. Joint equilibrium, if you go to joint B, Joint B is allowed to rotate. It is not fixed, so we are going to have joint equilibrium. How do we find joint equilibrium? If you remember in the method of moment distribution, whenever we come to a support like this, the moment we have on the left side is always equal to the moment at the right side, but opposite in direction. That means if we have an anti-clockwise moment here, we will have a clockwise moment here, the same magnitude, such that means that is what makes that joint to be at equilibrium. So with that, we can just come to say, if you stand at joint B, the moment two support moment you will have there, which will be MBA, that is MB going to A, and MB going to C, that is moment at B going to C and moment at B going to A. So that means you're going to have this MBA and MBC. And because you know those are the two joints that meet at this place, you're just going to say that MBA plus MBC equals to 0. So that is what we do. So that's why we go here and say at joint B, MBA plus MBC equals to 0. This is the moment equation we derive for MBA. This is the moment equation we derive for MBC. You equate them to 0. Now, if you simplify, remember this place is 0 because it's theta A. This theta D does not even come in this equation. So once this is 0, the two unknowns here is theta B and theta C. So if you simplify that equation, this is what we have: 1.5 EI theta B plus 0.5 EI theta C equals to minus 8. Call that equation 1. If you go to joint B again, the same thing can happen. The MCB plus MCD. So that means MCB plus MCD equals to 0. So you go again and say, similarly at joint C, MCD plus MCD equals to 0. That is MCB plus MCD equals to 0. This is equation from MCB and this is equation from MCD. Equate them to 0. And in this case, you can notice theta. This place was theta D, but it is 0 because theta D equals to 0. So you see, you have two unknown, theta B and theta C. If you simplify this equation, you now have the 0.5 EI theta B plus 1.5 EI theta C equals to minus 12. And this is equation 2. So if you have, we now have equation 1 and equation 2, which is this and this. If you solve them simultaneously using any method that is convenient with you, you will have that theta B equals to minus 3 over EI, while theta C equals to minus 7 over EI. So once we are able to find the unknown joint rotations, we now know theta A is 0. We have calculated the value for theta B, which is minus 3 over EI. We have calculated the value of theta C, which is minus 7 over EI. We know that theta D is 0. So what we do is to go back to this slope deflection equation, this equation, and put the value for theta A, theta B, theta C, theta D, wherever we see them. Once we go, that is, we do that, we will derive the joint equation, the joint moment. So that is what we are doing here. We go to the moment equation for joint for MAB, and it's still EI over L into 2 theta A plus theta B minus 40. So if we know theta A is 0, we know the value of theta B, we substitute them. That gives us minus 40.75 kilonewton meter. And we go to MBA. This is the equation. We just substitute 0 for theta A, minus 3 over EI for theta B, and it gives us 38.5. We do the same for MBC. Just substitute theta B, theta C, it gives you this. For MCB, substitute theta B, theta C, it gives you this. And this for MCD, this is theta C, and this is theta D, which is 0. And it gives you. For MDC, you do the same. Now you will notice that this is MB and this is MBA, and this is a okay, MBA doesn't have MBA. Where is MBC? This is MBC. So this is MBA, this is MBC. Remember that one of the equation, the first equation we derived, we say that MBA plus MBC equals to 0. So if you come here, this is MBA, 38.50. This is MBC, minus 38.50. And if you do this plus this, it will give you 0. So that means we are correct. That means at joint B, this plus this equals to 0. The same thing you can do at joint C. MCB plus MCD equals to 0. That's why this is 23 and this is minus 23.5. They will give you 0. And if you go back to the solution we solved in moment distribution, you will see that these are the joint moment. The valuation could just be later. Remember, this one was minus 40 plus 0.8, but here is 0.75. It's just due to approximation. The moment distribution depends on where you stopped. So this is it. So after this, the next thing is just to draw the bending moment and shear force diagram. And like I've said, once you're able to find the support moment, the rest is just the same, like moment distribution. So this is, if you have, for this beam we have, the principle is that you draw the support moment, which is this, and you draw the simply supported moment, which is this, and then you superimpose them. If you want more detail, watch part 2 of our video on moment distribution. You will see how we were able to handle this very example there. So if you go to the calculating support reaction, you just break the whole of this into different span, simple span. So if this span AB, span BC, span BC, put the support moment. Remember here we had minus 40.7, so an anti-clockwise moment. Here we have minus 38.5 and then 38. Okay, we have it was plus here and then minus here. This was plus 23.5, this minus 23, and this was plus 18.5. So when you put all the moment, you will just be analyzing each of the spans separately to have the support reaction. If you need more detail, like I said, watch part 2 of our video on moment distribution method. So with this, you're able to find the support reaction VA, and VB will be the two VBs. You add the two VCs to have the VC and this, and then you draw the shear force diagram. Just if you need more detail, go to our video on part 2 of our video on moment distribution. You will see how shear force and bending moment diagram was drawn for this particular exam. And so that is it for the solution of this. You draw the bending moment diagram. Now let's look at example 2. Analyze and draw the bending moment and shear force diagram of the beam beside indicating maximum span moment. You are asked to indicate maximum span moment. Of course, you have been doing that. So this again is the same thing with example 3 that we analyze using the method of moment distribution. So we are going to do the same here using the method of slope deflection. So the first thing is to write the fixed end moment. So we're not going to waste much time on this one. So fixed end moment at AB, this is a point load. Note that this point load is not at the midspan. So we are going to use PAB squared over L squared. Go back to that if you don't understand. PAB squared over L squared. That gives us this. This one will be P. Okay, that's for A going to B. For B going to A will be P A squared B over L squared. If you don't understand, just go back to this where we had this. This is a situation where you have a point load that is not at midspan. Go back and look at this. you will understand what we are doing there. So the fixed moment for span BC. Remember, BC is acted by 2.2 load, a UDL of 20 kilonewton per meter and a point load of 15 kilonewton at mid-span. So when you do that, you will notice that BC, at BC you have minus WL squared over 12 and plus minus PL over 8. So when you add the two, it gives you minus this. The same thing as CB, you will just have plus of the same thing. So you will have this. So this one is a UDL, so you can have the fixed moment. So after finding the fixed moment, note that there is no support settlement. That means delta is 0. So the next thing is to go and generate the slope deflection equation. So how do we do that from the slope deflection equation? At A, another thing you notice is only joint D that is fixed. So we have joint A, joint B, joint C. That means 3 unknown support rotation. Take note of that. So in this case, we will need 3 equations to solve them. So when we go to MAB at A is usually 2EI over L, but because I here is already 2, please take note of that. I here is already 2, so this is like 2EI. So the 2 multiplied by the 2 that is already there. That's why we have 2 times 2AI over L plus, of course, T2, theta A, theta B, the fixed end moment. When you go to BA, B going to A is 2EI. Please take note of this. This is the 2 that comes with the equation. This is the 2 that comes with the I in the span already. Then you derive the moment here. You do the same to BC, MBC, and when you're doing MBC, note that the I here is already 3I. So it's going to be 2 times 3EI over L. The same thing happens here in CB. But when you go to the span CD, that I is just I. So of course you go back to normal 2EI over L, 2EI over L. So when you derive the equation, take note that theta D is 0. In this case, it's only theta D that is equal to 0. So when you go there, you now do the joint equilibrium. Take note here that this is a simple support, and because it is a simple support, there is no moment. So moment at A is equal to 0. That means this MAB, that is the only moment at A, MAB equals to 0. So that is the first joint equilibrium. At joint A, you say that MAB equals to 0. So you just come, this is the equation for MAB equating to 0. So when you simplify it, this is what you will have: 1.6 EI theta A plus 0.8 EI theta B equals to 14.4. So this is equation 1. Then at joint B again, MBA plus MBC equals to 0. This equation for MBA, this equation for MBC, equate them to 0. And if you simplify, you will have this, which you call equation 2. And you go to joint C again, MCB plus MCD, that is a 2 moment at that support, equate them to 0. So this expression for MCB and this expression for MCD, if you equate them to 0, if you simplify, this is what you have. So you now have 3 equations. So what do you do with the 3 equations? You solve equation 1, equation 2, equation 3 simultaneously. We are going to solve it using the matrix determinant method. Matrix determinant method, to me, is the simplest method I can use. So write the equations. This is equation 1. Remember, equation 1 did not have a component for theta C. So we introduce and say 0 theta T. There's a reason for that. So this is equation 1, this is equation 2, and this is equation 3. Equation 3 did not have a component for theta A. So we introduce 0 theta A, which of course you will cancel. But we have a reason. So when we do that, we now represent this in a matrix method. in a matrix form, all of them in this side have EI as their component. So you can factorize EI and now bring out the component. For this equation, you have the component at this point is 1.5, the component here is 0.8, the component at this point is 0. You do the same for this and you do the same for this. That is how we were able to have this. And the three unknowns are this a column matrix of the three unknowns, theta A, theta B, theta C. And this solution 114.4, 2.78, and minus 0.38. This is what we use to have this column matrix. Once we do this, we can now go to start finding the determinant. The first one is to find the determinant of the square matrix, which is this square matrix. We find the determinant. So we call it delta 0. Delta 0. And this is the matrix that we want to find determinant. And you know the matrix method, if you cross this row and this column, so what you have here is 16 or 1.6, that's why it's 1.6 EI into, you now 5.6, this 5.6 times 5 gives you 28. EI is in all of them. EI will be squared minus. What you now have remaining will be 2 times 2, which is minus 4 EI squared. And you close the bracket. Now put this one. Remember, in matrix, you have to need to go back to look at how to find matrix determinants if you have forgotten. But when we come to here, we will introduce minus here. So this minus 0.8 EI. If you cross this and this, what you have is this. So it will be 0.8 times 5, which gives you this 4. Then EI squared minus, when you come here, 0 times 2, which is 0. When you come to the third one, because the what will be here will be 0. By the time you use to multiply, everything will be 0. So if you simplify this, it gives you 35.2 EI raised to power 3. If you simplify them. So the next thing you do is you find the determinant. You come to that determinant again. Remember this. The next one where you want to find the determinants for the one using theta A, you are going to replace the column, this first column. You are going to replace it with this one, the column that is for the answer. So this is what is done here. The whole of what was here has been replaced by that column. So if you do that, you go to the determinant process again. Find the determinant, and the determinant in this case gave us the 333.87. And so you will note EI squared, you will note and keep. To find the theta A will now be the determinant of the theta A all over the determinant of the first main determinant, which is delta theta A and delta naught. So this is delta theta A, this is delta naught. That's why we have 9.48 all over EI. You go to the one to do delta theta B again. To do delta theta B, this is column is for theta B. You replace this column by this column again. So that is why for delta theta B, the middle column is replaced by that answer, what we had in the answer column. So you find the determinant of delta theta B, and it gives us what? Minus 34.144 EI squared. So what we do is to find theta B, it will be the determinant of delta theta B all over delta naught, so which is minus this over this, it gives us minus 0.97 over EI. And so we do the same thing for theta C by replacing this last column with this answer column. So if we do that, this is what we have. We find the determinant delta theta C, it gives us this. And so when we find theta D, it will be delta theta C all over delta naught, That gives us 0.312 AI. So by doing this, we have been able to calculate the three unknown support rotation, that is theta A, theta B, theta C. Remember theta D was 0. So we go back to the moment equation that we had derived and substitute all of them. For this MAB, this is theta A, and this is theta B, and give us this. For MBA, this is theta A and theta B. It gives us this. For this is theta B, this is theta C, and it gives us. For this MCB, this is theta B, and this is theta C. For MCD, this is theta C and theta D, which is 0. And so by now doing so, we are able to find all the support moment. Again, if you take note, you will notice that MBA and MCB are equal in magnitude but opposite in direction. And you can see the same thing for MCB and MCD. So those are the things that tells you that what you're doing is right. And so the next one is to calculate the support reaction, which you're going to split this into simple span and impute the moment that we have calculated. Notice that moment here is 0, so there is nothing here. So you just will be taking moment at different using the concept of equilibrium to find the unknown support reactions. Again, we have solved this example before in using the method of moment distribution. That should be example 3. So if you need more detail, you can go to watch that video on moment distribution. So you'll be able to find that. So that should be on part 2 of moment distribution method. So you are able to find the support reaction, and the next thing is to draw the shear force and the bending moment diagram. So this is where we are going to end. I don't want the video to be too long. Thank you for watching. Please remember to subscribe to this channel and like this video if you have not done so already. Thank you very much.